Hello again. This is Math 1120 coming to you from the College of DuPage. The title of this lecture is Projectile Motion and Such. And remember to be an active learner as you watch this video. Here's an example of projectile motion. You have this gun that is shooting a pumpkin out of it, and it's shooting it at an angle. So this is the path, and the pumpkin is called a projectile. So we're shooting it off at this angle. Now notice that this pumpkin has, this is the vector representing its motion, but this is the vector, the x component, and this is the vector that is the y component. So you see we have at the same time for this pumpkin motion in the x and y directions. Now in low stakes assessments 9 and 10 we talked about in the x direction and in the y direction. Now we're putting them together, and this is determined to be motion in a plane. So here is the vector that is called vector r, and what we're doing is we're moving from a point that is considered to be a reference point of 0 to a point P, and r represents moving from the magnitude and direction from 0 to P. So that is r, and that's the position vector at point P. And certainly there are x and y components of r, and this is the path of the ball. And actually, if this were a ball, it would be going, but eventually gravity would start working on it and start bending down, and so on and so forth. As you recall, the magnitude of r is the magnitude of the r vector. We show that with these absolute value symbols, and that's the square root of x squared plus y squared. This is the Pythagorean theorem. Now we can also talk about the velocity though, because as we move from point 1 to point 2, there's a change in the r vector. It moves from this one to that one, so there actually is a change in the position in the r vector, and that's going to be the vector called the average velocity. So the average velocity is the change in position vector divided by the change in time, and this also then of course is a vector. And you see that the average velocity then is you're going from here to here over a given time, that's delta t, and there's going to be a y component and an x component of the velocity vector as well. So in fact, here's the definition of the average velocity. The average velocity of a particle is the displacement delta r, and that's the change in the r vector, divided by the time interval delta t. And so the average velocity vector is r2 minus r1 as vectors over t2 minus t1. So it looks like this. The numerator is a vector, the denominator is a scalar, so the whole thing is a vector, and velocity is a vector quantity. The units, if we have meters and seconds, is going to be meters per second, and it's always going to be length divided by time. Again, units are important. Some important notes. If the object is moving in the xy plane, then this average vector velocity has both an x and a y component, just like in the picture I showed you at the beginning of this lecture. If the object is moving only along the x-axis, then the y component of v average is 0. Similarly, if it's moving only along the y-axis, then the x component of the average velocity vector is also 0. We are not going to be talking about instantaneous velocities in this course, at least any more than just as a concept, because that involves the math subject called calculus, and that's not in the Math 1120 scope. So we're not going to be talking about instantaneous other than as concepts. And since velocity is a vector, the magnitude of the velocity is a scalar, and it's found using the Pythagorean theorem. It's the sum of the square of the coordinates, and when you talk about the magnitude, that's not telling, that removes the direction, It's just a number telling you how fast is it going. So that is the speed. So in my car, I could be going 50 miles an hour going towards Schaumburg, or I could be going 50 miles per hour going to Joliet. The speed would be the same. Now the direction of this vector, again, is given by the angle theta, which is the angle between, it's counterclockwise from the positive x-axis, and theta is going to be the inverse tangent of Vy over Vx. We studied this quite a bit in Chapter 1. Let's do a problem now. So we have a model car. For our first example of motion in a plane, suppose you are operating a radio-controlled model car on a vacant tennis court. The surface of the court represents the xy plane, and you place the origin at your own location. At time t1 equal 2 seconds, the car has xy coordinates of 4 meters and 2 meters. That's where the car is relative to you at time t equal 2. And at time t equal 2.5, it has coordinates 7 meters in the x direction and 6 meters in the y direction, again from you. So for the time interval from t1 to t2, the half second going from this time to this time, we're going to find the components of the average velocity of the car and the magnitude and direction of the average velocity. And here's a little picture that you can think about here, and you can see that the change in y was 4 and the change in x was 3 meters, and so that will help us as we go forward. Okay, so we want to find the components of that and use their definitions. So V average in the x direction is the change in x divided by the change in time. It's 3 divided by half is 6 meters per second. You see the units are meters per second. Similarly, the acceleration in the y direction, the average velocity in the y direction is delta y over delta t. So it is 8. And so those are the components that was what we were asked to find in Part A. Part B wants us to find the magnitude and direction of the average velocity. Well, the magnitude of the average velocity is the sum of the squares of those two. And so 6 squared is 36, 8 squared is 64. You add them together, you get 100 meters squared, second squared. The square root of that is going to be 10 meters per second. Now the direction is most easily described by the theta is the inverse tangent of the average velocity in the y direction divided by the average velocity in the x direction, and we get that this is 53 degrees. Here's kind of a concept problem. We'd probably poll on this if we were doing this in class. So consider two toy cars that are initially at rest at the origin. The cars begin to move at time t equals 0, and car 1 moves along the positive x-axis, and car 2 moves along a line that makes an angle of 45 degrees with respect to the positive x-axis. As they move, the x component of car 1's position is always equal to the x component of car 2's position. Which of the following statements is true regarding the average speed and velocity of the two cars? So there are 3 choices for you to consider. And we'll pretty much use a process of elimination here. The answer cannot be A because the cars are moving in different directions. So their average velocities can't be the same because the directions are different. Velocity is a vector quantity. And remember that the average velocity is a vector, so we must always account for its direction. Answer C also cannot be correct. Since car 2 moves at a 45-degree angle, the x and y components of its average velocity must be the same. That's true of a 45-45-90 right triangle. Its speed, which is the magnitude of its average velocity, therefore, is this one squared plus this one squared, but we said that those were always equal to one another. So that is going to be 2 times v average in the x direction whole squared. You take the square root of that and you get this. So car 2 is moving with a speed that is the square root of 2 times larger than that of car 1. So So the correct answer is B. Now, when we're talking about acceleration, acceleration is a change in velocity. And here you have a car that's going around a curve, and it doesn't change speed, but it is changing direction. That means there is an acceleration. This is called centripetal acceleration. And so even though there's not a change in how fast the car is going, there is a change in direction. So this is an acceleration. And so if we're doing V1 and V2, as we know, the acceleration is V1 minus V2 over delta t. And so when you look at these vectors, you see that this is the change in V2 minus V1 is this vector. Now the point you want to remember with centripetal acceleration is the acceleration is directed towards the inside of the circle. And here's the definition of average acceleration. So it is a vector. An object undergoes a displacement during the time delta t. Its average acceleration is the change in its velocity. Now remember, this is in 2 dimensions now, so this is delta v divided by delta t. So the average velocity is the vector, that is delta v, the change in the vectors, divided by c. The units are going to be meters per second squared. And even if a particle is moving at a constant speed, it can have a non-zero average acceleration if the particle changes the directions of its motion. So here is kind of a little concept test also. Can you spot the 3 accelerators in this picture? Well, almost everyone knows the gas pedal is an accelerator because if you press down on it, it makes the car speed up. But as a physics student, you probably also realize that the brake pedal is an accelerator. It slows the car down. The acceleration is negative. The third accelerator in this picture is the steering wheel, because if you change the direction, that changes the velocity. And so there is an acceleration. Again, calculus is out of scope, so instantaneous acceleration will only be talked about as a concept. And I think we talked about pretty much all of this before. The average acceleration in the x direction is the change in velocity in the x direction by t. The average velocity in the y direction is the change in velocity in the y direction divided by delta t. The magnitude of the average acceleration is going to be the sum of the squares of that magnitude. Again, it is a vector quantity. It's always going to be directed perpendicularly to the tangent, and this is how you would find the angle. And I think I really talked about all of that stuff already. So here's a problem. Let's again look at the radio-controlled model car. And suppose at time t equal 2 seconds, the car has this component of velocity. It is Vy is 1 meter per second, and that's Vx. V in the x direction is 1 meter per second, and V in the y direction is 3 meters per second. At the same time, we have, and at time t, 2 equal 2.5 seconds. Again, we're going from 2 to 2.5 seconds. The components are the velocity in the x direction is 4 meters per second, and velocity in the y direction is 3 meters per second. We're to find the components of the average acceleration and the magnitude and direction of the average acceleration during this interval. And again, you could look at this picture if you wanted to, and this is all relative to where you were starting the problem. So here is a solution. To find the components of the average acceleration, we need to find the components of the change in velocity. And so we're going to calculate. The change in Vx is 4 meters per second minus 1 meter per second, which is 3 meters per second. That is delta V in the x direction. Similarly, delta V in the y direction is also, and actually in this case, it is 0 because you see we don't change were the same in both of those, and so the change in Vy is 0. So when we sum the squares, we only get this, so the answer is just 6. Now part B, since there's only a x component, then the magnitude is going to be this, only in the x direction. Now here's a problem about an ant that visits you when you're trying to have a picnic. So an ant crawls at a constant speed on the top of a square blanket you've laid out for a picnic. You picked up a flat horizontal lawn, so it's all flat, and the blanket, one side runs north-south and the other side runs east-west. The ant crawls onto the blanket at the northeast corner and travels due west, and 60 seconds later the ant crawls off the blanket at its southwest corner, traveling south. At which direction does the average velocity of the ant for the 60 seconds it is on the blanket? And so you have choices of these directions. Well, the key idea is that the average velocity will point in the same direction as its displacement. So regardless of how the ant moved during those 60 seconds, what will happen is the ant's displacement will be from the northeast corner to the southwest corner. Therefore, the displacement points in the southwest direction, so the average velocity must point in the southwest as well. The correct answer is C. Here's another question. In which direction does the average acceleration of the ant point for the 60 seconds? And you have these choices. So even though the ant travels at a constant speed, the direction changes. So there will be an average acceleration over the 60 seconds. The average acceleration will point in the same direction as the change in its velocity by definition. And so the correct answer is going to be B, which is also southwest. In closing for now, more than ever, time is precious. Each day must count. Do the math, it will make you strong. And now, more than ever, take care of yourself and of each other. This lecture is continued in lecture 11.1.